Going to be doing day 6 notes of thermochemistry. This will be our last notes for this unit. And today we're going to talk about Hess's law. After today, you should understand how you can figure out the overall enthalpy changes or heat changes using Hess's law. This will allow you to add, multiply, divide, or reverse chemical equations to see the difference in the energy it takes to create a certain product or to put it into the reaction in the case of an endothermic reaction. So here's a flashcard for you to make. Hess's law is that if you add 2 or more chemical equations to get an overall equation, then you can also add the heat changes, or delta H's, to get the overall heat change. Stop the video for a second and go ahead and make a flashcard. So the steps to this, or the rules to doing this, the Hess's law, are pretty simple. Basically, you can think of this as a math equation where you're going to be just figuring out the overall change in the heat. So if you've got 2 identical substances that are on opposite sides of the arrow, one is a reactant and the other is a product, they're going to cancel out. If you have 2 identical substances on the same side of the arrow, which means that both of them are reactants, or you've got 2 of them that are products, you're going to add the coefficients together to get your reaction. You're going to keep substances on the same side of the arrow in the final equation. So let's take a look at how this happens. So when we're adding carbon plus oxygen to produce carbon dioxide, this is actually not just a one-step process. It can be reversed. Now, when we want to get this down so we've got the minimum number of moles, you'll notice that now we're using half a mole of oxygen. We only need one of those oxygen atoms to combine with our carbon monoxide to produce carbon dioxide. So when we have this balanced, we only need half a mole of oxygen. So make sure that you're aligning your arrows underneath each other. That's very important for visually being able to cancel these out. You can think of this again like a math equation. The first thing I'm going to do is I'm going to cancel out anything that's on both sides of the arrow. So carbon dioxide is over here, carbon dioxide is over here. I can cross those out and not consider them. Now, with the oxygen, I have 1 mole of oxygen that was here, but I only have half a mole on this side, on the product side. When I subtract those from each other, I'll be left with half a mole of oxygen gas. When I put these things together, basically anything that's not crossed off is just going to be brought down. This will be carbon plus the oxygen and the carbon monoxide right here. Everything else, notice, has been crossed off, so I don't need to write that in my final equation. And that will be carbon plus half a mole of oxygen gas will produce carbon monoxide. So let's look at when you're adding equations together. Here's 2 moles of copper plus 1 mole of oxygen gas will produce 2 moles of copper oxide. Here's another equation. If I have 4 moles of copper plus a mole of oxygen gas, I could produce 2 moles of cupric oxide. Notice that this has got a 2 coefficient, so I know that this has a different oxidation number than this one does. Now I'm going to look at these. These are the same, so I'm going to add them together. 1 mole plus 1 mole will be 2 moles. 2 moles of copper plus 4 moles of copper is 6 moles. Now, here I've got 2 different products. I've got 2 moles of copper oxide, and then I've got 2 moles of cupric oxide, so I have to put them both down separately because I can't just add them. They're different compounds. So if we're reversing chemical equations, all we have to do is just reverse the sign for the delta H, and then everything is all taken care of. Remember that heat is always conserved, so we're not going to lose energy when we're moving from one side of the reaction to the other. It's just whether the energy is going to be produced or whether the energy is going to be taken in order for the reaction to occur. So let's look at this. For a reversed reaction, all I'm going to do is I'm going to take the product side and move it over to the reactant side, and take the reactants and move them to the product side. Now, here we're given the delta H, a negative 574 kilojoules. So when I do the reverse reaction, my product is now on the reactant side, my reactants are now on the product side. All I have to do is take the delta H and reverse this sign. So my delta H for this reaction will be a positive 774 kilojoules. So reverse reactions are very easy to deal with. We just have to reverse the sign to say that instead of energy coming out, energy is going to be needed. Or the other way around. Now, if we have to multiply or divide a chemical equation, we're going to multiply or divide the coefficients, or the moles, by the same number, and also multiply and divide the delta H by the same number. So everything is just being consistent. If we're going to divide by 2, we're going to, in our equation, we're going to divide the delta H by 2 also. So if we're going to multiply equation by 2, here we have our equation with a delta H of negative 62.8 kilojoules. If I'm going to do this reaction and use twice as much of the reactants, I'm going to have the delta H will be twice the size. So this gets multiplied by 2, which will give you 2 moles of calcium plus 4 moles of carbon. Will give you 2 moles of calcium carbonate. And then I'm also going to multiply my delta H by 2. And that will give me the heat change that's just twice as big as what the reaction was when it was balanced and reduced down to the lowest coefficients. So you can rearrange and combine these reactions. So here's an example of this. If you're reversing and multiplying by 3, you're going to do a reaction that's 3 times bigger than it would be if it was just a balanced chemical equation with the coefficients all reduced. So here we have 2 moles of iron. Now we can do this by, remember with the coefficients here, we need 3 oxygen, we need 2 of the iron. So when we're doing this, we want to consider we're using 1.5 of the units of oxygen, so that we have 3 oxygen atoms, so that it will be balanced off over here. So we take this, remember this is a reversed reaction, so we're just going to put the products over on the reactant side, the reactants over on the product side, and multiply everything by 3. When we do this, we get 3 moles of iron oxide with 6 moles of iron. And again, if you reduce this down, you'd get a whole number. But we're just going to leave it as a fraction right here, because all we're doing is multiplying by 3. 3 times 3 is 9. 3 times 2 is 6. We've got everything balanced off here. Multiply our delta H by 3, reverse the sign, and here's the amount of heat. So this reaction will actually produce 2,472.6 kilojoules of heat. So let's apply this to some examples. So if we're asked to find the delta H for C2H4 plus H2, which will produce C2H6, there's one of our reactions. You're going to be given the following information. In order to produce our C2H4, here's the delta H. In order to produce C2H6, here's the delta H. So I've got a negative number and a positive number. When I put these together, here's this, I'm going to reverse that reaction, which will give me a negative 52 kilojoules. Here's my product, and here's my product. And I have to, it's going in the same direction, so I don't need to worry about reversing it. Making sure my arrows are lined up so I can cross things off. I've got 2 moles of carbon, 2 moles of carbon that will cancel out. I've got 2 moles of hydrogen gas. That 3 is going to get crossed off with, I'll still have 1 mole of hydrogen gas. This will be the overall reaction when I combine these together. And now all I have to do is add these numbers together. A negative 52 plus a negative 85 is going to be negative 137 kilojoules. Here's another example. Find the delta H for Now you'll need to have the following information. Take a second and stop the video and see if you can do this problem by yourself, and then check your answer with mine. Alright, this is slightly more complicated, but still the same procedure. The first thing we have to do is look to see what we have. So in order to, we have 6 moles and 1 mole here. We're going to multiply this by 6. So there's my reaction. I'm going to multiply my delta H by 6. I guess my circles are a little bit off center there. So I've got 2 moles to 1 mole, so the reverse reaction I'm going to multiply by 2. So there's the reverse. I switch the products over into the reactant side, the reactants to the product side. Multiplied it by 2. Remember, I had to reverse the sign because this is a reversed reaction. I've got hydrogen on both sides. I can cancel those off. This is what I'm left with. So here's my final reaction. The last thing I do is combine these terms together. If you have a negative 552 kilojoules plus a positive 92 kilojoules, that will leave you with a negative 460 kilojoules as the energy change. So that's the end of this video. Let's go ahead and practice some of these. You're now going to move to the practice station, where you can work through a couple problems with me.